that I will bring up a later period having to do with a couple of rather specialized examples of continuous distillation. But I'll take them up at a later period when we have occasion to discuss some other specialized applications of distillation designs, which are both continuous and discontinuous. For example, I'll mention what some of them are, but I'll hand you out a diagram later. For example, in the distillation of Scotch whiskey, in Scotland, they use two methods of distillation. One is continuous distillation, or the so-called patent still whiskey, in which they originally changed over part of their production from pot distillation to use of continuous distillation in a particular type of still called a coffee still, after the man's name Coffee, who invented it and patented it. Well, in a way, it's a continuous distillation column with a stripping column and a concentrating column, but it has some rather unique features or aspects, such as using the feed stream of wine or beer to be distilled. Passes through a series of coils that goes back and forth across every plate in the concentrating column, so you have a variable reflux ratio as you come down the column, because the wine is being preheated, condenses some of the vapor, and of course entering at the top it condenses more of the vapor than it would at a lower level in the column. And but otherwise, that coffee still is very much like the split column arrangement we use here in California. But I won't say more about that until I hand out a diagram about it a little later. At the same time, we could have talked about pumice dealcoholizers, or pumice stills of the type that handle the solid pumice. And again, I'll postpone the discussion of that till I can create a little diagram and discuss it. Then along about the same time, I'll be able to hand out a drawing of a cognac alembic, or a pot still, and one of the process that they use in Armagnac, where they have a pot still, but it's also a pot rectifier, and the wine is entered continuously, but the dealcoholized wine is drawn off intermittently. So it's sort of a combination of steady state and non-steady state. So anyway, today I thought we'd take up a theoretical aspect of batch distillation. And so this little 4-page handout here is an outline of what we intend to cover this morning. Recalling now that we classified distillation into two general types, steady state and non-steady state, and then we considered single stage and multi-stage. So now we're to the point of considering the non-steady state, or more commonly referred to as batch or pot distillation. Now, in a theoretical treatment of this, we consider that when we take a charge of a liquid indicated by L and cause some of it to be vaporized by the application of heat, that the vapor is evolved in equilibrium with the liquid at any point in time, at any moment. And since it's since the concentration of the vapor evolved and the liquid involved will be varying continuously with the passage of time, or between various states in the operation, we can treat it as a differential, on a differential basis. So the term differential distillation is a theoretical term which is equivalent to a single-stage batch distillation. I mention this and emphasize this because the word differential is sometimes confused with the term we use, equilibrium distillation, which is the comparable term for a single-stage continuous process, or equilibrium distillation being synonymous with flash distillation. Well, anyway, by a simple development here, as I've given in this handout, we can develop an expression which may seem a little theoretical, but in practice it's actually very useful to have. I might preface these remarks by saying that batch or steady-state distillation is, as we've already indicated, is a process that's used in practice in production of distilled spirits. Very notable examples being the production of cognac in France, and second being the production of the pot still, or the old all malt whiskies as they're called, in the Highlands of Scotland. But I'll discuss those in detail a little later. So anyway, a mathematical expression that pertains to the process of differential distillation is known as a Rayleigh equation. So on this first page here, I've set about to derive the equation, and it's done in a rather simple manner. By first considering that we create a differential quantity of vapor from a given charge of liquid designated by the letter L. And so if we say that we've produced a differential quantity of vapor dV of composition Y, the quantity of the liquid will have decreased by a quantity dL. So considering it now from the standpoint of a volatile component, the quantity of volatile component removed in this differential quantity of vapor dL is of course equal to the decrease in the volatile, is equal to the decrease in the amount of the volatile component in the equilibrium liquid. So at any particular point in time, the quantity of volatile component in the liquid is Lx, whatever the liquid quantity happens to be, times the concentration at that particular moment. So the term minus d Lx would represent the change in the amount of volatile component in the liquid as a result of the removal of differential quantity of vapor dV of composition Y. So in effect, we write a mass balance again with respect to the more volatile component in differential equation form. And so you have the derivation there at the bottom of the page, minus d parentheses Lx is equal to Y dV. And since dL is equal to minus dV, or dV is equal to minus dL, we can write minus Y dL. So expanding the expression where both L and X are our variables, we have L dx plus X dL is equal to Y dL. So that's a form of a differential equation which is obtained by writing a mass balance with respect to the volatile component. And rearranging that, we can come up with the expression at the bottom of the page that dL over L is equal to dx over Y minus X. That is the differential expression of the Rayleigh equation, but in its integrated form, as shown on top of page 2. We come out with the final Rayleigh equation form. So we're considering that we're going to sum this equation up between two finite states, 1 and 2, which would represent the states between the passage of a finite time. For example, state 1 might be the initial state, and then after you've operated for a given period of time, then we want to consider the state number 2. And so then we integrate between states 1 and 2, or in other words, between the time when we have L1 and the time quantity of liquid L1 and later quantity L2. When the composition of the liquid has changed from the initial, what might be considered the initial quantity, initial concentration X1 to a final concentration X2. So putting those limits onto the integral expression and integrating. Well, integration of dl over L, or dx over x, is equal to the logarithm of x. And so this reduces down then to the expression logarithm of L2 over L1 is equal to the integral of dx over y minus x between x1 and x2. Or if you want to write it in the reverse form, since L1 is usually larger than L2, if we're considering it as initial state, we'd write the reciprocal, so it would be logarithm of L1 over L2 is equal to integral from x2 to L1, from x2 to x1 times dx over y minus x. So this is the Rayleigh equation. Now, so now in order to solve this thing for any practical cases, we need to have some expression between y and x. And in most cases, this is available only as the equilibrium data, a table of data, or a graph. In limited and special situations, the relationship of y to x may be expressed algebraically, but most often this only applies to very dilute solutions where Henry's law applies. We've already indicated several times where the relationship between y and x can be expressed in terms of a Henry's constant, k. So if you substitute kx as the value of y in the Rayleigh equation, you come up with an expression of dl over L is equal to dx over k minus 1 times x. And so here again, since on both sides of the differential equation you have the general integration of the term, the style dx over x, it becomes then integrated. The logarithm L1 over L2 is equal to 1 over k minus 1 times the logarithm of x1 over x2. But as I say here, in the more general case, the equilibrium relationship is not really expressible algebraically. So the solution to problems of differential distillation requires generally a graphical solution, graphical integration, where we can plot x versus 1 over y minus x and integrate graphically. This is about the only application of calculus that I can recall we apply in this course, but anyway, and it's a rather simple application. But anyway, if we want to solve an expression such as given there by a graphical integration, what do? Suppose we have some sort of a curve which represents the relationship, in this case we want between x and y minus x, 1 over y minus x, looking at the original Rayleigh equation form up in the middle of page 2. If we plot 1 over y minus x And we're interested in evaluating the expression, the integral of dx over y minus x. Why, what are we doing here between two limits, x, let's say x1 and x2, or x2 and x1, whichever way we want to write it, where x1 might be this and x2 this, because if x1 precedes it, it's usually a decreasing value. So what do we do? If all we're doing is, in integrating, is summing up the product of a little differential segment of x dx multiplied by the variable on the vertical scale, which is now 1 over y minus x. So when you integrate, we simply are in effect adding up all the area under the curve between these two limits. In other words, when you add all these little thin segments of dx times 1 over y minus x, well, you have the value of the integral, the summation in that, right? Okay. So, this is how we do it. Now, I've got a problem set here, one of which requires this kind of a solution. So let's think for a minute how you would practically carry this out. How would you graphically integrate? How do you measure the area under the curve, which of course represents the function logarithm of L1 over L2? So how would you do it? You could take a set of XY data and plot a curve. Well, you have to really take the table of data and then subtract the y from x and take the reciprocal, and then you plot the reciprocal of that difference against x, and then you have the representation of the curve that we want to make the integration. So anyway, how would you make this? How would you measure this area under the curve in practice? Quantitatively. Now we're trying to get a quantitative answer. How would you do it?
Draw squares.
Count squares. All right. That's a very good answer. Sometimes it's the easiest way to do it. Although it becomes a little laborious sometimes, but you can approximate it very well by counting the squares. On a graph paper where you have large squares and then smaller squares, it's not so bad because you can count all the large squares that are not intersected by the curve, and you know how much that is in a hurry. And then you can go down and count the smaller squares and determine how many of those are. And so it's not too difficult. Yeah, anyone suggest some other ways of doing it?
Cut it out and weigh the paper.
Right. This is a very good way. As a matter of fact, you make the assumption that paper is uniform, so you can cut this out with a pair of scissors, and put it on analytical balance, and let's say weigh a certain amount here. Let's say between limits, the whole area, and then weigh and then cut out the part on the curve and weigh that, and this fraction of the total area, this weight fraction of the total weight would represent the part on the curve of this expression of these quantities here of x1 minus x2 times 1 over x1 up to whatever the limits are, where you make your reference. You can do it here, that level, or here, wherever it is. Usually that'd be the logical place to cut it out. I'll show you an example of that in a minute, a little later. Any other methods of, that you know about integrating?
computer to do it, maybe.
Graphically. Well, there is a little instrument called a planimeter that can be used. I've got one, but when I looked for it this morning, somebody borrowed it and hadn't brought it back, so I'll see if I can find it and show it to you. But it's a little device where you roll it along carefully along the paper, and the little roller, as you trace the curve from start back all the way back to the origin, will count up the area in reference to, let's say, some other designated area. So then you get the fraction of the curve by just tracing it carefully along. It takes a little practice to use a planimeter and have to check it to make sure it didn't slip on the way or a few things like that, but it can be used. To go on momentarily to a special case of batch distillation, which has some application. I might say that in general, this concept of batch distillation may have several applications in a laboratory, perhaps more so than in a plant. Many times you have a question of making some batch distillation in a laboratory for either an analytical method, carrying out some analysis, or maybe preparing some material on a small scale. So I've given you a special case of batch distillation which involves continuous stripping. And the principle here is illustrated by the application of this principle to the determination of acetic acid in wine, or the volatile acid in wine. Whereas I've drawn here a little simple sketch of a volatile acid tube where you put a sample in the inner part of the tube, and then you create steam in a steam generator, at the bottom of the flask below it usually, and pass this steam through the liquid, and the vapor is carried off and condensed and collected. And as you know, the standard procedure is to take 10 milliliters of wine and distill off about 100 milliliters of distillate. And why is that necessary? Well, it's because of the volatility of acetic acid is relatively low, so you have to apply the principle of steam stripping and provide considerably more vapor than the original volume of liquid. So you can treat this quantitatively if we know the equilibrium constant between the y and x as indicated here. So the way this is treated mathematically is that here we first consider L as the original mass of the sample. For all practical terms, it could be the volume, since the density is not going to change very much in dilute solutions. But anyway, basically it's considered mass of the sample. Lx then would be the mass of acetic acid in the sample, if we're talking about acetic acid. Then make the assumption that the amount of steam introduced is equal to the amount of vapor evolved. Now, right at the start of the analysis, of course, this is not true, because momentarily you're condensing some of the steam to heat the liquid up to the boiling point. But as soon as that happens, then you get the vapor going off somewhat more rapidly than the steam, because the heat of vaporization of alcohol is a little less than half that of water. So initially, when you're distilling off mostly alcohol, well, you'll get a greater volume distilled off for the amount of steam put in, so it tends to compensate. But anyway, after a few seconds, or half a minute perhaps, we almost exactly have that the amount of vapor leaving the tube is equal to the amount of steam entering it. So if S is equal to V overall, why then L, of course, remains constant. The L stays constant in the tube. So, treating it as a differential, on a differential basis here, we let a differential quantity of steam be introduced, which produces a dV quantity of a vapor removed by writing a material balance of the volatile component, in our case acetic acid. We'd have minus dLx as before. That represents the decrease in the amount of the volatile component, or the component in question, in the liquid upon the removal of a differential quantity of vapor dV of composition Y. And then on top of page 4, since L is a constant, why the differential equation comes out to have this more simple form of minus L dx is equal to Y dV. And so you have a form which you can, where now in integrating, you have a one that comes down to where you have minus 1 over L is a constant times the integral of V1 to V, integral of dV from V1 to V2 is equal to integral of dx over Y from whatever limits x1 to x2. And again, where for dilute solutions, where Henry's law is applicable, in this case y is equal to kx, so that you substitute that directly in there. And so you end up with an expression that the change in volume, or V1 minus V2 divided by L, is equal to 1 over K times the logarithm of x2 over x1. Now, in the literature, the author, Altschiller and others, which is the same reference that we have in the case of, one of the references we have in the case of the ethyl alcohol water vapor-liquid equilibrium data. They give the value for acetic acid in water, and that for less than 1%, it's constant at about 0.695x. Y is equal to 6.95x on a mass basis. So, pardon? 0.695. I apologize for this reproduction. The Xerox was a little weak this morning, and that constant is 0.695 in the middle of the page there. So if we want to apply this to the volatile acid determination, and if we want to consider that V1, the initial is 0, that in other words, we really want to measure the change in volume of distillate between V1 and V2, or in other words, consider V1 is equal to 0. X1's initial concentration of the volatile acid component, of the volatile component, and X1 is the residual concentration. So, substituting in, we have V2 over L is equal to 1 over 6.95 times the logarithm x1 over x2. So that would be the general expression. And now then, if you want to get a 9.95% recovery of acetic acid in distillate, I just took this as an example and assume that x1 is 0.10%, which is about the upper limit, which is constant applied, but also be toward the upper limit of the concentration of acetic acid you're interested in determining. Standard wines, anyway. X2 then, of course, if you're going to recover 99% of that, would be 1/10 minus 0.995 times a tenth, or comes out to be 0.0005% would be the residual concentration in the liquid for 99.5% recovery. Substituting that in, you come up with an expression that V2 over L is comes out to be, solving the logarithm, comes out to be 7.62, which says then that V2 is equal to 7.62L, or in other words, in order to get 99.5% recovery, you need to distill about 7.6 times as much as the original volume of liquid taken. In practice, that is, we routinely distill off about 10 times as much. So I solved it, but didn't show the solution here down at the bottom. The corollary would be if V2 over L is 10 to 1, then X1 over X2 comes out to be about 1,040 to 1, which gives a percent recovery of 99.9%. So in other words, that's adequate for the analytical procedure. So then a little problem set which I'd be pleased if you'd consider. And there's three problems there. The second and third one are the two easier ones of those, so I'd ask you to work those out for next period. And I don't think it'll take too long to work those. And then we would ask you to work this first problem, or complete the first problem by let's say next Wednesday, the day after. Now I think you recall, I think you'll recall that when I handed out this table earlier in the quarter of the equilibrium data for ethyl alcohol water mixture at atmospheric pressure, I wrote in longhand in the last two columns the function of y minus x on a weight percent basis or mass percent basis and the reciprocal value. So I've already worked it out for you as far as this function here is necessary to plot this curve. Now this particular problem that I handed out, the first one said that the charge to a simple pot still is 20% by weight. That would be 20% here. And by differential distillation, the alcohol content is reduced down to 1% here. Now, what fraction of the charge is to be distilled? Or in other words, using the integral expression, the logarithm of L1 over L2, or better, easier, it's L2 over L1. No, L1 over L2, that's the way to do it, the way it's given there. Determine what fraction of the charge has to be distilled. Or in other words, the ratio of L1 over or really L2 over L1. Now, it is the other way around that I would normally the way you do it. In other words, you want to integrate the the other way around. Since L1 is larger than L2, or you can consider that as 1, then whatever L2 value is, that's the fraction remaining, isn't it? And the max amount distilled would be 1 minus L2. And of course, from that case, then you integrate from x1, from x2 to x1. Since x2 is larger than x1, the way the problem is stated, by then, of course, you have positive values on both sides here. The other point I was going to make in connection with this is that it's not necessary to plot your curve beyond the value of x greater than 20%, because that's all you're interested in from there on down to 1%. So these values on here, you don't have to plot the beyond 20% in working the problem. That is 20% x. Here, for example, is my solution to this problem, where, see, I originally cut it out. I really cut it out clear up to here. Originally, it wasn't necessary to do that. It would have been better to cut it out right here. But I weighed it, and I put the weight on the back, weight on analytical balance. Then I cut out this lower portion here, the part under the curve, as you see here, and weighed that. Got the value, so that gives the fraction under the curve of the total. And so that would be the fraction of the amount represented by the square, whatever you take out, weigh out. The total square. Well, any questions about that? There is another way. There is another way of integrating this, and I got here at gives a pretty close approximation to the integration. That is to for some particular value, say at each unit value of percent alcohol by weight, that you multiply, you read off that value of 1 over y minus x, and then just kind of add up a little table here. For various values of 1 over y minus, for various values x, the value of 1 over y minus x. And if you take it for each unit value of percent alcohol by volume in the liquid, each unit value of x, why then you really are summing up 20 different little small steps, which are a little broader steps than the dx thickness, but anyway, it approximates the value pretty close. Do you see what I mean? In effect, what we're doing here is taking this distance here times this height here. So in effect, we have a little error on the right-hand side, a little too much, a little too little on this side, but they tend to compensate, except perhaps at the value x equal 1, where the curve is rather steep. So you can make a little graphical compensation for that, come out with the right answer. So I worked that problem 3 different ways and get almost the same answer each time. I would say that then let's consider very briefly then the second aspect of or the fourth type of distillation, that is batch or or non-steady state distillation and multi-stage. Well, this is accomplished by combining a simple pot or a boiler with a fractionating device, or in other words, a plate column. And so in essence, the equipment that you use to conduct this would be some sort of a pot or boiler, which you introduce the liquid. And then we put a plate column on top here, either on top or maybe set off the side where the vapor is carried over to it. And the vapor from that, of course, goes off to a condenser. And if the fractionating column here is going to perform any function, then we've got to return some of the liquid back as reflux or overflow. So we could we can determine, just in the same fashion as we did for continuous distillation, at any particular moment how many trays it would take to create a certain concentration of distillate from a certain concentration in the liquid. Because if you write at any moment in time, write a material balance like we did for continuous distillation, you come up with exactly the same equation. And so at any particular moment in time, we could, if we want to, let's see, if we want, how do I want to do this? We can say that for a given reflux ratio, this is an equilibrium curve, If we started with an at any particular time, if this was the concentration in the pot, X sub L, let's say state 1, at a given reflux ratio, we could, by stepwise manipulations, determine, let's say if we had 1, 2, 3 equilibrium stages in the pot, equivalent to 3 equilibrium stages in the column, rather, that this would be the, I should have said this X of distillate, X of D. If this is the initial distillate you were going to expect to get, this is the initial X sub L in the pot, which would produce that, see, at any moment in time. So, in other words, you can operate a pot rectifier in two different ways. Obviously, if you continue the, if you operate a column and continue to at constant reflux, you'll have, as a result, you'll have a varying concentration of the distillate. It'll be a certain value at the start, and it'll decline, and the average composition of distillate will be some average of that, some aggregate average. So if you use constant reflux, you'll have variable product composition. And so if you want to obtain a certain specified final product concentration, well, you have to have it operate in such a way that it'll be higher at the start. And so the point to which it declines will be averaged in and give you the final resultant value. For example, at some later point in time, the composition of distillate 0.2 for the same reflux ratio, you would have this value in the pot, and so on. The other way of operating it would be to operate with a variable reflux ratio or an increasing reflux ratio.
That, on the second line, you just do the second operating line of the exit. That's the same slope as the first one, right?
Yeah, same slope. It's intended to be. These are the same slope. Now, the other way in which a pot rectifier could be operated in order to give a specified product concentration would be to operate at an increasing reflux ratio for a given number of ideal stages in the concentrating column. And this would be illustrated by at two different points in time by something like this. This is the curve again, and and let's say this represents the desired distillate concentration, X sub D. Initially, you can have a rather low reflux ratio, perhaps, where you have a, let's say if you had this many, and had 3 stages. Oh, I guess I'd need one more. 3, that'd be 1, 2, 3. No, I got 4 in there now. Well, anyway, that's all right. If this represents, this would be X sub L1. Now, as the concentration decreases during the run, as you take them out more in the volatile, in the vapor, well then you would have to increase the reflux ratio. So at now we'd have we'd have that many. We'd have this would be the concentration in the pot, which would enable you to get this distillate concentration with this reflux ratio. You see. Of course, it should be apparent that at some point, at some value here, you reach the minimum concentration in the liquid in the pot, which would be able to produce that concentration even at infinite reflux ratio, or that is a total reflux, I mean. So one could, if I ask you the question, what is the minimum concentration of alcohol in the pot in order to produce a given distillate? Why, with a say, let's say 3 or 4 or some specified number of ideal stages. In that case, you take the number of steps between the curve and the diagonal. Or in other words, that'd be the the minimum value. Well, of course, in practice, this means that you have a lot of an infinite number of combinations of the two that you can use in operation. Some people may find some advantages in let's say, perhaps starting out at a high distillate concentration, and perhaps in order to get heads removed more effectively or in a more concentrated form. And then you would, in order to decrease the concentration of alcohol, well, you decrease the reflux ratio, in effect, by drawing out more product and drop the concentration down pretty quickly. So let's say they're maybe 170 proof. And then you'd carry along maybe at more or less constant reflux ratio for a variable length of time until it's obvious that you're not going to be able to hold that much longer. You have to have too high a reflux ratio. Well, then you'd cut it off and collect tails portion then, and then probably decrease the reflux ratio so you'd get the tails over more quickly where you're not interested now in holding the concentration up. So I did have a couple of charts illustrating these, but in fact it's very similar, a little bit better drawn than the ones I sketched on the board. Maybe I'll hand those out to you at a later period.
You said that if we were given the X of D and the number of ideal steps, and we wanted to find the minimum amount of alcohol in the liquid, then we wouldn't use an operating line, and the ideal steps would be drawn from the intersect on the diagonal to the equilibrium curve, and then right back down to the diagonal.
Yeah.
There's no operating line in that case.
Well, the diagonal then, or total reflux, becomes the operating line as the limit. It's sort of a comparable concept to the minimum reflux ratio we had before. You'd approach this as you'd approach that value as a limit by taking the steps between the curve and the diagonal. So if you had this many, in this case, this would be X sub L minimum that would produce this distillate composition even at total reflux, you see. There's approach total reflux. Well, in other words, to work out problems where time, over a period of time, where you have where you have variable conditions here, it becomes rather complicated, as you might see, or you can get into very complicated situations. But it's not easy to visualize what happens at a point in time during a batch distillation run, as you can see here. Maybe I'll have a little more to say about this, but that's about all I'm going to have to say about batch distillation from the theoretical standpoint. So that'll be all for this morning.